Welcome to Stepwise Regression. Stepwise regression is a method to strike a balance between the complexity of a regression model and the ability of the model to approximate empirical data. Stepwise regression finds this balance by adding or removing candidate predictors from the data. If there are multiple candidate predictors, the best model might not contain all of them. Using fewer predictors can have benefits. For example, there is a lower risk of overfitting. That is, using only few predictors generally results in models that fit well to more datasets than only the one we used for fitting the model. Less parameterized models are also more consistent with Occam's razor, which is a philosophical principle that states that simple explanations are better than complicated ones. Model selection is the selection of a subset from the set of candidate predictors. Backward elimination and forward selection are stepwise regression methods for model selection. There are many possible criteria for deciding whether a variable is a meaningful predictor. Our textbook discusses two criteria: selection based on the adjusted R-squared and selection based on p-values. On the one hand, we use the adjusted R-squared to select variables that increase predictive power at the cost of possibly including statistically insignificant variables. On the other hand, if we are interested in selecting variables that are statistically significant, then we use p-values. However, selection based on p-values does not necessarily maximize predictive power. Let us discuss model selection based on the adjusted R-squared in more detail. To understand the purpose of the adjusted R-squared, please recall that the unadjusted R-squared in multiple regression is defined as 1 minus the ratio of the residual sum of squares to the total sum of squares. When a predictor is added to a model, the residual sum of squares cannot increase and usually decreases. Consequently, it is pointless to maximize the unadjusted R-squared. Let me show you an example. Suppose we have a dataset with n outcomes. We can obtain R-squared equal to 1 and thus the maximum R-squared with the following model. First, we create n-1 binary 0-1 dummy variables that uniquely identify each observation. Then we perform ordinary least squares regression. For example, consider a dataset that shows the approval ratings of President George W. Bush in an international poll reported by Associated Press on the 14th of December 2004. You can download the file from the URL below this video. The first column of the spreadsheet shows the approval rating in %. The second column shows the country where the poll was conducted. There are 4 different countries, so we can encode the same information with 3 dummy variables: country is Canada, country is Germany, and country is Spain. Let us import the data and remove the column with the country names. Next, we fit a linear model that predicts the approval on the basis of the dummy variables. As you can see in the console output, the multiple, that is unadjusted R-squared, equals 1. This value is the largest possible unadjusted R-squared, but the model is meaningless because it is tantamount to saying that the outcome of each observation must be treated as its own special case. Such a model cannot explain or predict any observation that is not already known from the start. The motivation for adjusting the R-squared is that if an additional predictor does not reduce the residual sum of squares, then the predictor should be removed from the model. The adjusted R-squared is a measure of a model's goodness of fit that accounts for the number of predictors k by inserting a factor n-1 divided by n-k-1. If k increases, then the ratio of the residual sum of squares to the total sum of squares tends to decrease, whereas n-1 divided by n-k-1 increases. A good compromise is obtained by a model that maximizes the adjusted R-squared. Finding the combination of predictors that maximizes the adjusted R-squared becomes difficult if there are many candidate predictors. Backward elimination, based on the adjusted R-squared, is an algorithm that selects a model with a large adjusted R-squared, but the selected model does not necessarily achieve the maximum adjusted R-squared. Backward elimination starts with a model that includes all potential predictors. This model is sometimes called the full model. Next, the the algorithm determines the predictor that, if dropped from the model, leads to the highest non-negative increase in the adjusted R-squared. If it is impossible to achieve a non-negative increase by removing any single predictor, then the algorithm stops and returns the current model as the result. Then the predictor identified in step 2 is removed from the model. If there is still at least one predictor in the model, the algorithm goes back to step 2. Eventually, there will be either no predictor left, or no elimination of a single predictor yields a larger adjusted R-squared than the current model. Let us consider a dataset about auctions on eBay in which the game Mario Kart for the Nintendo Wii was sold. You can download the data at the link below this video. The spreadsheet contains 5 columns: the total price, which equals the auction price plus the shipping price, a dummy variable for the condition of the Nintendo Wii. True stands for a new, false for a used console. The third column is a dummy variable that shows whether the auction's feature photo was a stock photo or not. A picture was considered to be a stock photo if it was also used in other auctions. The fourth column shows the duration of the auction in days. And the fifth column shows the number of Wii wheels included in the auction. These are steering wheel attachments that make it seem as though the user is driving in the game. First, I import the data. The dummy variables are encoded as logical vectors, that is, the elements can only be true or false. When performing regression, true will be automatically converted to the number 1 and false to the number 0, so it is not necessary to make the conversion from the logical to the numerical data type ourselves. Before proceeding with regression, we need to look at a scatter plot matrix to check whether the assumptions of linear regression are satisfied. Because many data points overlap, I apply a small amount of jitter and make points semi-transparent. Let us first check whether there are outliers in the quantitative variables. Evidently, there is no far outlier in the distribution of price. The existence of outliers is more difficult to judge for the variables duration and wheel, which can only take small integer values. I wrote a function called hist and box, which places a box plot above the histogram. Here is the combination of histogram and box plot for duration. According to the usual definition of an outlier as a value that is 1.5 interquartile ranges away from the edges of the box, there is no outlier in duration. The same applies to wheels. We conclude that we do not need to worry about outliers in this dataset. The scatter plots do not exhibit strong multicollinearity. They do not show clear signs of curvature either. However, after we selected a model, we still need to check whether the residual plot is reasonably straight. How about homoscedasticity? The scatter plots do not thicken. Some box plots show 2 unequally large boxes, but the difference in spread might be an artifact of the discretized numeric predictors duration and wheel. After selecting a model, we will make a QQ plot to confirm that the distribution of residuals is nearly normal. Next, I define a function called adj_r_sq that takes a formula as input and returns the adjusted R-squared for the corresponding model. The purpose of this function is to reduce the amount of typing in the rest of the script. Now we take the first step in backward elimination by calculating the adjusted R-squared of the full model, 0.7108. Next, we calculate the adjusted R-squared of all models that have exactly one predictor less than the full model. We can remove predictors from our formulae with the minus operator. The largest adjusted R-squared, 0.7128, is achieved by removing duration. Because the adjusted R-squared has increased compared to the full model, the algorithm now permanently drops duration from the model. In the next step, we calculate the adjusted R-squared of all models that drop duration and one more predictor. All models lead to a lower adjusted R-squared, so backward elimination stops and returns the model in which all variables are predictors except duration. We still need to check the residual plot and the QQ plot of the selected model. The residual plot reveals some curvature. However, the effect is small compared to the spread in the distribution of residuals. The QQ plot is nearly straight, so the distribution of residuals is nearly normal. We conclude that the selected regression model satisfies all assumptions of linear regression. Our summary of the model reveals that a used Nintendo Wii with a stock photo and no wheels is predicted to cost $36.05. If all other conditions are kept the same, then a new Nintendo Wii tends to be $5.18 more expensive than used ones. An auction with a stock photo tends to lead to a price increase of $1.12 compared to auctions without a stock photo. For every additional wheel, the price increases by $7.30. It is surprising that the coefficient for stock photo is positive, because a purpose-made photo should give the buyer greater confidence about the quality of the item. However, at a significance level of 0.05, the coefficient for the stock photo is not statistically significant. Therefore, backward elimination based on p-values instead of the adjusted R-squared would remove stock photo from the set of predictors. Still, stock photo makes predictions more accurate, which explains why backward elimination kept this variable as a predictor. I recommend you try out backward elimination based on p-values to see the difference. Our textbook also explains how to perform forward selection instead of backward elimination. Please read the textbook carefully and, afterwards, confirm that forward selection based on the adjusted R-squared yields the same model as backward elimination based on the adjusted R-squared. However, do you think that forward selection always produces the same result as backward selection? This question is implicit in the following task. I will leave this question visible on the screen while ending this tutorial. Please first try to answer the question yourself. Afterwards you can find the right answer in the text below this video. Have fun with the question and see you soon.